friends, today we shall be discussing about computation of critical drift. We have already discussed regarding how to compute normal drift, and also we have discussed about the concept of specific energy, and today we shall be going to see how we can calculate or how we can compute the critical drift and how these things are coming into use in our different hydraulics calculations. Well, before going to this, let me just recapitulate what we did in the last class. Well, we started with concept of specific energy, and that means just to recall that specific energy is nothing but energy per unit weight of fluid, flowing fluid rather, per unit weight of flowing fluid with respect to channel bed. So, this is what we call a specific energy, and then we discuss about the specific energy diagram. Well, this specific energy is a function of the drift. So, if we plot the drift and the specific energy, that diagram basically we call as specific energy diagram. Well, and then we did discuss about another diagram that we call as a drift discharge diagram. Well, for a given specific energy, we can have a relationship between the discharge and the drift. So, that diagram, that is for a constant specific energy, we get a single line, for drift and discharge a curve we get rather, and then again for a different energy level we get different lines. So, a set of curve we get, that we call as a drift discharge diagram. Well, then again we did discuss about critical drift, which is very important. Today we are going to discuss about the computation of critical drift. So, critical drift is the drift which corresponds to the minimum specific energy. Well, so we got specific energy, and then we could see that for a particular depth of flow for a given discharge, the specific energy in a channel become minimum, and that particular depth is called a critical depth. Well, then we got another term that is called alternate depth, that also we did discuss. What we mean by alternate depth, that for a particular specific energy, that means in a channel we can get a specific energy for two different depth. For two different depths we can have same specific energy, and these two different depths are called alternate depth. I mean, one of these two depths is in the supercritical region and another is in the subcritical region. And so, when the flow is in subcritical condition, then for a particular depth, suppose we are getting a specific energy, then for the same specific energy we can get another depth when the flow is in a supercritical region. So, that way these depths are called alternate depths. So, that also we did discuss in our last class, and then we talk about another term that is called critical slope. Well, when a channel is carrying a particular discharge Q, say, then for a particular slope we can have uniform flow. For a particular slope we can have uniform flow at critical depth. We know that critical depth is already defined, and so we know that this is that critical depth, and in a channel for a particular slope we can adjust the slope and we can have a slope where we are having uniform flow for a particular discharge, and that uniform flow depth is equal to the critical depth, and so that particular slope we refer as critical slope. That means critical slope is the slope where uniform flow occur with critical depth. Well, now when the slope of the channel is flatter than the critical slope, then we call this as mild slope, and when the slope of the channel is steeper, when the slope of the channel is steeper than the critical slope, then we call that as a steep slope. So, that way we got critical slope, we got mild slope, then we got steep slope. Well, after that we did discuss the condition of critical flow. That means, how we will understand that flow is critical. Well, we can define that minimum specific energy means it is critical flow, but how we will understand? So, we need some definite index to show that okay, it is the critical flow condition, and basically one condition is definitely that when specific energy is minimum for a given discharge, that is called critical flow condition. Then another condition is that when Froude number, suppose in a channel we are observing the velocity, we are observing the depth, and then we can very easily calculate the Froude number, that we all know what is Froude number. So, when that Froude number is unity, then we call that is the critical flow condition, that we did derived in the last class. Similarly, we could see another point also. For a given specific energy, discharge is maximum at critical flow condition. So, that is also another condition. Then we got another point related to that kinetic energy is half of the hydraulic depth. So, that sort of relation also we did obtain. And then we got another point, that is the, of course, we did not discuss in detail that point, but still we just mark that point, that the specific force, of course, specific force is minimum at critical flow condition. So, all those different conditions we got for critical flow condition, and which indicate that the flow is critical. Now, we came to, after that we came to computation of critical depth. Rather, computation of critical flow means computation of critical depth. So, we started with that, we end up our last class with that computation of critical flow, and there we could see that for a trapezoidal channel, if our channel is of trapezoidal shape, then we could see that we get a relation which do not permit us to calculate the critical depth directly or explicitly, we cannot calculate, and in that case we need to go for trial and error procedure. So, let us start from that particular point, that is computation of critical depth. Well, so you can concentrate into the slide. When it is trapezoidal channel, then we know that very basic relation for critical depth is q square t by g a cube. This is equal to 1, that we did derived in the last class. And if it is a trapezoidal channel, like this, then we get that q square t, that is the top width t. If the side slope is z, then the top width t is b, that means the bottom width b plus twice of zyc, So, this part and that. That way we are getting this q square t by g, and a cube, this a cube, if we write on this side, then area is b plus zyc into yc cube. So, a cube. So, that is what we are getting, and this equation, from this equation it is clear that we cannot have this in the form that yc is equal to some other known term. So, we cannot calculate it directly. Well, what we can do then, for this sort of trapezoidal channel, we need to go for trial and error procedure. We put some critical depth value and we try to see whether the left hand side and right hand side is matching or not. Then if we keep, and then we keep on changing this one, and we try to get a value of yc by trial and error procedure. Well, that procedure is definitely tiresome and time consuming. Of course, now with the advent of computer, we can get it very easily, but otherwise if we go for hand calculation, this is really problematic, and that is why some graphical procedures were also developed. So, we have some graphical procedure, and then in the graphical procedure we use a term that is called section factor. In the computation of normal drift also we got a term called section factor, which is basically coming from the sectional dimension of the flow section, and here this section factor also we use, but this section factor for critical depth computation is not the same expression that we got for normal depth, it is a different expression. So, if we start from this relation q square t by g a cube equal to 1, then we can write it that q square by g equal to a square into a by t. So, that is giving us, we know that a by t is nothing but hydraulic depth d. So, as a by t is equal to hydraulic depth d, so we can have that it is equal to a square, that is area square into hydraulic depth, and that we can write as q by root over g, taking square root of both sides, we can write as q by root over g is equal to a root over d, and this particular expression is called section factor z for critical depth computation. And using this section factor, in fact we can find this section factor if we know the q and g is of course known. So, once q is given, we can find this value, and then we have some graphical plot from which we could find the critical depth value. But however, nowadays these are not used that much. The basic reason is that we have computer, we can go for trial and error method very easily, and that is why these methods are not having that popularity as it had earlier. Well, so then similarly from this expression we can see, we can rewrite this expression that z is equal to a root over d, a is also a function of y, and d hydraulic depth is also a function of y. So, that way z square we can write that a square into d what we had. So, that we can write as c, one coefficient c, and then y to the power m, this is the depth. So, that way this relation, from this relation we are writing it in terms of one exponent m, that is called hydraulic exponent m for critical depth computation. And just as a information, I am just sharing these things, that this sort of relations are used using this hydraulic exponent m, and then plotting it, this expression again in graphical form, we could solve for the critical depth. But as I am telling that nowadays we have other easier procedure. So, we normally do not go for this sort of graphical procedure. Well, then from this particular slide we could see that computation of critical depth, of course, we are talking about the expression what we are getting for trapezoidal channel, and for this sort of channel computation of critical depth we cannot get directly, and that is why we are talking about all this graphical procedure or trial and error procedure. But is it the same situation for other shape of channel? That is, if our channel is say rectangular, if our channel is say triangular, then what will happen? So, let us just see what sort of expression we get for solving critical depth in these different type of channel. Well, first let us talk about rectangular channel. So, this is a rectangular channel, and then say this is B bedwidth, and if this depth is YC, that is the critical depth. Okay. Now, starting from the very general relation q square t by g a cube is equal to say 1. This is a general expression for critical depth. So, we can start from that, and here our top width t is nothing but equal to the b. So, what we can write that this implies q square, then we can write it as b and g, and area is nothing but b into y c. So, we can write this as b cube into y c cube, this is equal to 1. Okay. So, this area cube, and from that we can write it in a different form. So, this b cube and b is there. So, it can be written as q square by b square and g, let it remain like that, and 1 by yc cube equal to 1. Now, this q square by b square, that term can be written as in the term of unit discharge. So, discharge per unit weight, that is q is the discharge. So, per unit weight means q by b, that can be written as unit discharge, and symbol used for that is small q. Well, so this can be written as q square by g, and that can be written as equal to yc cube, or this implies that yc is equal to q square by g whole to the power 1/3. So, that way for a rectangular channel we can see that we can calculate the critical depth yc directly if we know the q value, small q, or say capital Q if we know, and if we know the b value, bandwidth b, then we can directly calculate this critical depth yc is equal to q square by g whole to the power 1/3. Well, and one important point, it is though it is obvious that we need to mention, or rather if we mention this is better, that for a channel, if someone asks that a channel is carrying this mass of discharge and it is having this much of slope, what is the critical depth? Normally when someone asks to compute critical depth, many students have seen that it thinks about the slope. Here basically critical depth is not depending on the slope. So, critical depth is not a function of slope, rather it is, we can calculate the critical depth as in terms of q and this g value. So, that way critical depth can be calculated directly. Well, now let us see another relationship. Let us see another relationship. At critical condition, suppose the channel is flowing in a critical, so water is flowing in a channel with critical condition, that or at a particular section we have a critical depth. Now, what is the energy at that point? We know that energy or the specific energy is minimum, that is known. But I mean, can we express that energy in terms of, that critical depth? Because we know that energy is a function of y, depth y. So, at critical condition, can we have a definite relationship between this specific energy and the depth? Well, let us just explore that. So, in this slide we will be discussing about, that is, E versus Y relationship for critical condition, and this we are discussing for say rectangular channel, as we are starting with rectangular channel. Well, we know that that is why say relationship of critical depth yc and specific energy we are meaning, but specific energy we can always write as E minimum, because this particular condition we are talking about minimum specific energy, because it is the critical flow condition. Well, so we can start like say E minimum is equal to y c plus v square by twice g, y c plus v square by twice g. As we are writing E minimum, so we are writing here y c, we are writing here critical depth. Well, then v square, that we can write as v is nothing but equal to q by area, and for rectangular channel this is nothing but q by b into y c. This is always critical depth. So, this is equal to, we can write as q by b, that part we can write as q by y c. So, this part we can write that this is equal to y c plus v square, we can write as q square by y c square, and then it is twice g. from this expression what we can write, that yc plus, we had one expression q square by g. So, I am keeping it like that, and again I am writing 2 into yc square here, this part I am writing here. And q square by z, if we go to our previous slide, we could see that q square by z, this expression q square by z is nothing but yc cube. So, this q square by z we can write as yc cube, this is plus. So, this is equal to yc plus yc cube by 2 yc square, and that will lead us to say yc plus yc by 2, yc plus yc by 2, and that can be written as, all these we are writing about E minimum. So, this is nothing but we can write that 2 3 by 2 into yc. So, yc E minimum we can write as E minimum is equal to 3 by 2 into yc, or this can be written in the form that yc is equal to 2 by 3 E minimum. So, once we know the energy E minimum, then we can calculate the yc directly from this, or if we know the yc, we can calculate E minimum directly from this. So, this relation show that there is a definite relation for critical depth computation or for computation of minimum specific energy in critical condition. Well, now let us see if our channel is not rectangular, rather say it is a triangular channel. It is a triangular channel. Well, so let me draw a triangular channel. Suppose we are having flow y c, and then side slope is z. Well, so this top width here, it will be, say this part will be z y c, this part will be z y c. So, total will be twice z into y c, and this z is basically we are writing about the side slope z. Okay. So, in triangular channel, again if we start from the very basic relation, that is q square t by g a cube, and area we can write as half of base into altitude. So, base of this triangle is twice z y c, and altitude is equal to y c. So, this is equal to z y c square. So, area we can write like that, and so q square t by g a cube equal to 1, that will lead us to q square, then top width is equal to twice z into y c, and then it is z, and area we can write as z y c square whole cube, z y c square whole cube. Now, from this we can express y c in terms of the other value, So, let us try doing that. It will be y c cube, y c to the power 6, this part will be, and this is 1 y c. So, ultimately we can write y c to the power 5, y c to the power 5 is equal to q square, then twice z, and here it will be g and z to the power cube. So, finally, we can have it in the form that q square twice q square by g z square. So, y c to the power 5 we are getting in the form that twice q square by g z square. Okay. And using this relationship, again say yc is equal to twice q square by zz square whole to the power 1/5. Okay. Now, this relation we can use for computing critical depth directly. So, in a triangular channel, if the side slope z is known, q is known, then we can directly calculate the yc. Now, let us see can we have some relationship again for computing minimum specific energy or specific energy at the critical condition, that on the basis of this critical depth. Well, so this slide we will be discussing about E versus Y relationship for critical condition in triangular channel. Let me again start from, say, E is equal to specific energy E minimum, we are talking about E is equal to yc plus v square by twice c. Starting from that, we can write it as yc plus v square is equal to q square by a square, and that a square relationship as we could get here, that we can see is zyc square. So, we can write zyc square whole square and then twice g. And we just need to remember what relationship we got for this yc, So, that is yc is equal to twice q square by zz square. Yc we got as twice q square by zz square, yc to the power 5 rather, yc to the power 5 is equal to twice q square by gz square. Now, we need to express this particular expression to have this expression, that is this expression twice q square by gz square, so that we can have it in terms of yc. So, let us just rewrite this in this form, y minimum is equal to yc plus, if we write here twice q square, just to have it in this form, we can write here another 2, and so it will become 4. Then this zyc square is already there. So, let me write it as z square, and then g is here, and yc I am writing separately, yc to the power 4. Well, so twice q square by zz square, that expression we are getting here, and that expression is nothing but it is yc to the power 5. So, we can rewrite this expression as yc plus yc to the power 5 divided by 4 yc to the power 4, and this is nothing but equal to yc plus 1 by 4 yc or yc by 4. Okay. And that we can write as 5 by 4 yc, 5 by 4 yc. So, E minimum we can write as 5 by 4 yc. So, that is another relation that we can have for triangular channel, or yc is equal to 4 by 5 E minimum, 4 by 5 E minimum. Well, from these two analyses we could see that for triangular channel and for rectangular channel we can express minimum specific energy, that is the energy at critical condition, in terms of y. Now, if it is a parabolic channel, let us see what sort of expression we can have, or can we solve it directly? Can we solve critical depth directly for parabolic channel? Well, so let us take a parabolic channel like this, and in parabolic channel, if this depth is yc, then this top width can be expressed in terms of yc as, say, k some coefficient and yc to the power half. This is our top width. This is the top width. from the very basic expression of parabola, we can write it like that. Top width is equal to k yc to the power half, and the area that we can write as area is equal to 2 by 3 k yc to the power half, that is what the top width, and into yc 2/3 of. So, this become equal to 2 by 3 k yc to the power 3 by 2. So, that is the expression for area, and k is a constant of the parabola. K is the constant of the parabola. So, using this expression, again if we start from the very basic relation, that is q square t by g a q is equal to 1. If we start from that again, then what we can write, q square and t top width is nothing but k yc to the power half. So, q square t, then g a cube we can write as 2 by 3 k yc to the power 3 by 2, but this entire expression will have to be power to q. So, this we can again simplify, rather our basic objective is to find out yc. Well, let me write one more step here, that is q square k into yc to the power half g, then this 2 cube means 8 divided by 27, and then we can write k cube, and then this will be yc to the power half, yc to the power half. Okay. Sorry, this will be yc to the power 9 by 2. Okay. Now, from this, if we write the yc directly, this is equal to 1, and from that let me go this side, that is yc to the power 9 by 2, and if it is coming here, then it will be 8 by 2. So, it will be yc to the power 8 by 2, or we can write yc to the power 4 directly, yc to the power 4, this expression, this yc and this yc combining, it will be yc to the power 4. This is equal to q square by 8 by 27 g, and this k and k, it is k square. So, that expression we are getting, that is yc to the power 4 is equal to q square by 8 by 27 g k square. Well, now using this expression, can we again just find one relationship between the minimum specific energy and the y and the critical depth yc. Again we need to recall this relationship. This can be written in this form also, yc is equal to 27 by 8 q square by z k square whole to the power 1/4. This can be written like that also. Okay. Now, let me go to the next slide and see how we can calculate yc, or how we can express yc in terms of minimum specific energy. Well, again minimum specific energy, E minimum is equal to yc plus v square by twice g. So, yc plus v square is nothing but q square by a square and twice g. Now, let me write this a square term, and let me have this term here, so that readily we can write it. It is area terms is equal to 2 by 3 k yc to the power 3 by 2. So, area is equal to 2 by 3 k yc to the power 3 by 2, k yc to the power 3 by 2, and the other relation, that is yc is equal to 27 by 8 q square by z k square. q square by g k square whole to the power 1/4. Okay. Starting from that, what we can write, this implies E minimum is equal to yc, and let me again rewrite this expression in the form so that we can write yc for this particular expression, yc plus say q square, let it remain like that, and then area we will be writing as 2 by 3 k yc to the power 3 by 2 this square and twice g. So, this is equal to yc plus this we can write as 4 by 9 k square and yc to the power 6 by 2, that is yc cube, and then it is twice g, and then q square is remaining there. Well, so this expression, if we just try to write it in this form, then we can just write it like that, yc plus, it will be 9 by 4, but we need to get it as 27 by 8. Okay, let me write it as 9 by 4, and then it is q square and k square, g is there. So, this 2 and this 4, this will become 8, 2 and 4, this will become 8, and then this is yc cube. Okay. But still, to express this in the form, that is 27 by 8, we can write it in the form that yc plus this we will write at 27 q square, then 8 k square g, this part is there, and then we will multiply it by 3 yc cube. So, finally, this expression we can combine and we can write this as yc plus this part is again yc to the power 4. So, ultimately it will be 1/3 of yc, and this can be written as 4 by 3 yc. So, the expression can be written as E minimum is equal to 4/3 of 4 by 3 yc. 4 by 3 yc. Well, so this is one relationship that we can have for a parabolic channel, as such, we can see now that the computation of critical depth is not always very difficult. Rather, for most of the cases like rectangular channel, like triangular channel, and then like parabolic channel even, we can get it very directly. That is, if we know the discharge, if we know the channel section, then we can get the critical depth expression directly. So, computation is rather easy as compared to the computation of normal depth. Only for trapezoidal channel we need to go for trial and error procedure. Well, let me go to the another important relationship. We have seen that yc can be calculated, and thus energy at that yc can also be calculated, and if we just recall our specific energy diagram, it was like that, and then you can just concentrate onto the graph. Then for a specific energy E, we can have two depth, say this is y1 and this is y2. We can have two depth y1 and y2, and these two depth we call as alternate depth, other than the minimum specific energy. When it is minimum specific energy, then the depth we get is called critical depth. This is what our critical depth. This is what our critical depth, but other than minimum specific energy, if we go to any other energy level, then we get two different depth for a specific energy for a given discharge q, and these two depth, one is in supercritical condition and other is in subcritical condition. And now let us see, can we derive some relationship between the critical depth and these alternate depths. So, in this slide we will be discussing about relationship between critical depth and alternate depth, relationship between critical depth and alternate depth. Well, let me write that as in these 2 point energy, specific energy is equal. So, what we can write, that is y1 plus, suppose velocity corresponding to this point is, this depth is v1. So, y1 plus v1 square by twice z, and that is equal to y2 plus v2 square by twice g. Okay. So, from this we can write that y2 minus y1 is equal to v2 square by twice z, sorry, v1 square by twice z minus v2 square by twice g. Okay. Now, for rectangular channel, what we can write, for rectangular channel, this relationship is very popular, and for rectangular channel we can have this in this form, that is, if it is yc, then this velocity v at any point can be written as q. Basically, first we can write it as area into q by area, we can write it as q by area, and this is velocity equal to q by area. Area is nothing but b into y c. So, this can be written as q by yc, q by yc. Okay. So, writing this, whatever may be the velocity, see here the velocity is v1, and in the second section velocity is, or in the when the depth is higher, velocity is v2. Definitely this v2 will be less than the v1, but the discharge, that is the unit discharge or the discharge of the channel is not changing. So, if because we are talking about this particular line, we are talking about this specific energy line for a given discharge. So, when the discharge is same, and if it is a prismatic channel, then our B is also same. So, that way this q, the small q is not changing. So, whether it is V1 square or V2 square, that we can write as in terms of q square by yc, q square by yc and twice z minus q square by y1 rather. At this point it will be y1, at the other point it will be y2, q square by y1 minus q square by twice z into y2. So, taking this advantage, what we can write, that we can write as 1 by twice z, q square by twice z, rather we can write q square by twice z, and then it is 1 by y1 minus 1 by y2, 1 by y1 minus 1 by y2. Oh, here I did a mistake, because this is v square I am writing, v is equal to q by y1. So, v square is equal to q square by y1 square, and this is equal to y2 square. So, it will be y1 square minus y2 square. So, this can be written as, again we know that q square by z, that particular expression is nothing but yc cube, if we recall our earlier expression. So, q square by this can be q square by z can be written as yc cube, and then it will be 1 by 2, this part is y1 square y2 square, this will be y2 square minus y1 square, and that can be written as that can be written as y2 minus y1 into y2 plus y1 divided by twice y1 square y2 square, and this here on the left hand side we had y2 minus y1. So, this y2 minus y1 and this y2 minus y1 if we cancel, then we can write that this yc cube, we can write as a yc cube is equal to this part twice y1 square y2 square divided by y2 plus y1. And so, this expression finally can be written as yc cube is equal to twice y1 square y2 square divided by y1 plus y2. So, this is one of the very popular expression that is used when we want to know that what will be the suppose if we know that a particular depth we have y1 and then we want to know what is the alternate depth, then if we know the critical depth we can calculate that, or suppose we know the y1 and y2 at a particular energy level, we know that this is y1 and that is y2, then knowing y1 and y2 also we can calculate critical depth. That is why while we are discussing the computation of critical depth, we are discussing this relation as well, because this can be used for computing the value of critical depth. Well, then let me discuss another topic very briefly. Of course, this topic is critical depth in compound channel, and this need to be discussed very elaborately, but it is beyond the scope of this particular course, and that is why just to give you some idea or just to have some discussion on this topic, let me just discuss it briefly. Well, let us draw one compound channel and let us see how we can have some peculiar relationship for critical depth computation in compound channel. In fact, Chaudhary and Balamudi in 1988 did this sort of analysis for symmetrical compound section. By symmetrical compound section, what we mean that these are identical, this left hand side, right hand sides are identical. This is a compound channel, and then say depth of flow at any level, maybe y here, then this B we can write as Bm, that is the main channel. And always we know that in a compound channel, when the depth of flow will be less or the discharge will be less, then flow will be concentrated, or sorry, the flow will be flowing through the main channel. And of course, concentrated flow goes through the flow concentration is always in the central part, and then on the side the flow will be less, rather the flow velocity will be less. And then this level we call as depth up to the flat plane, YF, depth up to the flat plane, and this portion is called width of the flat plane, BF, and as it is symmetrical, so this side also it will be flat plane width, the same BF. And so far Manning's roughness is concerned, here we can write that this is an M main channel roughness, this is say flat plane roughness. And then in the compound channel, using this term, some non-dimensional term can be derived, say YR, that is equal to Y, depth of flow at any point, divided by YF. This is say non-dimensional term regarding depth. And then we can have breadth related non-dimensional term, that is equal to flat plane width, divided by say flat plane width divided by width of the main channel, Bm. Then we can have another term Bf, this is equal to Bf divided by Yf. Then we can have this Nr, that is equal to Nm divided by Nf. Now, this is just non-dimensional term which is used for obtaining or for analyzing this critical flow computation. And of course, as I have already mentioned that we do not have that much of scope to go in detail of this analysis, but still we can have some of the understanding. Well, now we know that yc, as we have already discussed, say yc is equal to, we can have q square by z, yc cube is equal to q square by z. So, if it is q square by z means small q is equal to q by b, and when we talk about this rectangular portion, that is the lower portion of the compound channel, this lower portion of the compound channel, this particular portion, then it is just simple rectangular channel, and we can have this expression, that is q square by g, that q square we can write q square by b square, small q square. So, q square by g, and yc cube is equal to q square by g. So, this is a bm. Now, this we can write as at a critical condition, it is like that, yc q is equal to. So, this can be written as g bm square then yc cube by q square is equal to 1. I mean, from that we can write this one. Now, let us see if for a particular discharge, if our critical depth lies below this channel, below this flat plane depth, then we can use this expression directly, because up to this point we do not have nothing like compound channel. Here it is just simple rectangular channel. Now, we can calculate if in place of yc, that means up to yc is equal to yf, if your yc remain yf, then we can have this sort of relationship. So, we can write one expression, that g bm square then say yf cube by q square. Let us define this as k. Let us define this as k. We can define this as k. Now, this expression, from this expression we can have some understanding that if, say if our k is equal to 1. So, k is equal to 1 means yc, this implies that yc is equal to yf. Now, if k is less than 1, if k is less than 1, k less than 1 means what we can write, k less than 1 means yc, that is it is less than 1 means yf is less than yc. So, yc is greater than yf. Well, now what it indicate, yc greater than yf. So, yc greater than yf means critical depth, if you just refer this diagram, critical depth will be greater than yf, that means greater than this particular depth. So, when critical depth is greater than this particular depth, that means we cannot have critical depth below this main channel and below the flat plane level, and in that case that will not be valid, because up to this portion only we can have rectangular. So, this we can consider this as a rectangular channel. So, this implies that critical flow cannot occur, this implies critical flow cannot occur within the, let me write, critical flow cannot occur in the rectangular portion, in the rectangular portion. Okay. Now, if we have another condition that k is greater than 1, okay. So, k greater than 1 will indicate yf is greater than yc. Now, if our flat plane depth bf, if our flat plane depth yf is greater than critical depth, that means the critical depth will occur or critical flow will occur within the rectangular channel. So, this will lead us to that condition that critical flow occur critical flow occur in the rectangular portion, Well, so when critical flow occur in the rectangular portion, then this we can calculate directly. Now, when critical flow is occurring somewhere here, when the flow is over flat plane, that means from this analysis what we are getting, that if the flow is critical depth is occurring, or rather flow is occurring above the flat plane, then only, that is when the flow depth somewhere here, then we can have some complexities in computing critical flow. When it is below this, yes, we can do it directly. And for that, another term was defined, that term is called C, which basically relate, that is YR, BR, those non-dimensional relationship BF and NR. And this C, I mean, when our this K expression is equal to C, then we can have critical flow condition. Well, and that C we can plot like this, that means on this side if we plot YR, basically for a section, for other things remaining same, say our BR, as we could see, just to again go back, BR is equal to BF by BM, it should be written BM, sorry, BR is equal to BF by BM. So, as we can see that this BF, BM, suppose for a given section, if these are constant, BF, YF, these are constant, but this YR will be varying with the depth. That means, when depth changes, YR is varying. NM and NF, this NR ratio is also remaining same. So, ultimately from this expression, if for a given section, for a given roughness, everything remaining same, C become a function of YR. So, we can plot YR versus C, and C and YR will start from 1. If you just go back to this expression, YR is nothing but Y by YF. So, when Y is equal to YF, this Y is equal to YF, the depth of flow is this much, we are getting it below the rectangular portion. Now, our point, or we are now interested when it is above this thing. So, when Y will be exceeding this YF, then YR become higher than 1. So, when it is higher than 1, then we are interested what will happen, then we are talking about this term C. So, this is say 1, this is 0, 1, 2, 3, if we get like that, and depending on the section we can have different sort of curve. This will be 1, say 1.1, 1.2, that way the ratio is gradually increasing, and then we can have a curve like this. You can have a curve like this. And then when we calculate the K value, that K value what we got earlier, this K value, and then if we see that in this curve K can be greater than, there we are getting a value C max, maximum value of C for a given section. If our K is, suppose K value we are calculating and K is greater than C max, this can be one condition, say this is case 1. Case 1 we are getting K is greater than C max. Then we can have another condition that, okay, now here we can see when case 1 K is greater than C max means this on the flat plane, when the flow is above flat plane, we are not getting any intercept of this K value with the C max. That means it indirectly means that no critical flow will occur, in the upper portion of the compound channel, because we are talking about upper portion of the compound channel as our YR ratio is higher. So, no critical depth will occur in the upper portion of the compound channel. Well, critical flow will occur only in the lower portion of the compound channel, that is the condition. And when we have, say, if our case 2, if we can have this K is less than C max, and we can have K is greater than 1, that means it is above 1 and is less than C max, means somewhere here this K value. Now, if it is like that, that means we are finding there will be one critical depth where K is equal to C, here one point, and this is above the flood plane, YR ratio 1.1 and 1.2 between. So, it is higher than that. So, at some point it will be there. Then another critical depth we are getting here, where it is just slightly higher than YR is slightly higher than 1, means just near the flood plane, we are getting these things. If I draw this compound section, that means YR is just greater than 1, means just here somewhere we are getting one critical depth. Say YC, we are getting one YC, and another YC we will be getting here, which correspond to this value. So, this condition indicate two critical depth will be there above the flood plane, 2 YC above the flood plane, So, that is what we are getting. And of course, as K is greater than 1, from this condition we got, when K is greater than 1, there will be another critical depth below the flood plane. So, 2 critical YC and 1 YC below flood plane. So, that also we are getting. And then we can have another case 3, when our K is less than C max and also K is less than equal to 1. That means, if we are coming below this one, then it is going like this, and we are getting one critical depth above the flood plane. So, this will lead to one critical depth above the flood plane, Okay. And obviously, as K is less than 1, we will not get any critical depth below the flood plane level, and that is why from these conditions we can see that there will be a, if we draw the specific energy diagram, this is a flood plane level, and for case 1 there will be no critical depth here, and there will be change in the diagram, and this is the critical depth. This is case 1. And then for case 2, what will happen? There will be one critical depth here, and then energy diagram is going like that, and then it is coming like that. So, there will be 3 critical depth, 2 above the flood plane and 1 below the flood plane, 1, 2, 3, and here it is only 1. And for the third, this is case 2, and for the third case, what will happen? There will be a critical depth above the flood plane, but there will be no critical depth below the flood plane. This is what one critical depth. So, that way in compound section we can have 3 critical depth condition, 3 critical flow condition, and for all these specific energy is of course minimum here, specific energy is minimum in the case 1, specific energy is minimum for 2 cases in the case 2, but for one case specific energy is not even minimum. So, these sort of different conditions we can have for computing critical flow in compound channel. Well, this much is I think sufficient to have some understanding of critical depth computation in compound channel. In the next class, we will be going more detail into the critical flow computation. We will be solving some numericals, and that way we will try to see how critical depth computation can be done for different types of channel, and how this critical flow computation helps us in studying other aspect of hydraulic engineering. Thank you very much.